Hello everyone, and welcome back to another professional prep video. In this video, I'm going to show you the third and final step of solving differential equations using using separation of variables. So, if you missed the first two videos, I'd go ahead and check those out. They will cover the antiderivative step and the separation of variables step. And those will lead you into these two equations that we have here, partially solved differential equations. Now in this video I told you that I was going to finish off these equations and talk about two different types of solutions, general and particular. So general solutions, I'm going to do one of each in this video. General solutions are solutions to differential equations where we cannot solve for this constant c, and thus the solution will have c in it. It will be in the form y equals something something plus c. And we won't know what c is. Versus particular solutions, we're given a point called an initial condition on the solution, so we will be able to plug that in for x and y and to solve for c. So our final solution will be y equals something something and no plus c. We will have to solve for the constant. So now that you know the difference, let me start with the general solution example. So you will recognize these two equations from our previous video. There was a third one on there that I will leave for you for practice to find the general solution if you feel that you would like some more practice. If you want practice with a particular solution with that, then take the solution 1, 3. And you'll know more about what that means then, but that'll get you some practice if you want it. But let me start with the general solution problem. So, as I said, there's no way that we can solve for c here in a general solution. So this is going to be about just using algebra and algebraically, manipulating this equation so that it becomes in the form y equals something. So you'll start recognizing patterns as you do more and more of these, but basically we want to try to get rid of this ln of y. So what we're going to do with that is we're going to exponentiate with e, because the e and the natural log will cancel out, and that is our goal here. So doing that will cancel things out. So what I'm going to do is I'm simply going to put e and imagine these as exponents. So that'll be more clear in the next line. The e and the ln are going to cancel out, and now we are just left with the absolute value of y. And remember that whenever your antiderivative has natural log, the y, or whatever variable it is, needs to go in absolute value, because you cannot take the natural log of a negative value. That's a domain error, so you need to be careful with that. So that will be absolute value of y equals e to the 2/3 x cubed, and note that this whole 2/3 x cubed plus c expression is in the exponent of e, so that's very important for this. And now, I did mention that we wanted to try to have y equals, so we don't want to keep the absolute value there. Now, since we don't know what c is, we can't just remove it, but what we can do is we can just do y equals, and then put a plus or minus here, and then you would choose this based off of whatever makes the domain fit. But here we cannot do that because we don't have the initial condition. So this right here, oh, I'm sorry. I did not mean to do that, but this is a good thing to learn from, that needs to stay in the exponent. You cannot bring that down. And that's everything. So this is actually, and that's it. This is the general solution to the differential equation. And to see the original equation, please feel free to tune into one of our previous videos, and that'll give you the steps for getting to this point as well. But that's it. We have solved this equation. And please note that this is all in one level, 2/3 x cubed plus c. So the writing did not come out great, but that's all in the exponent of e. And we had to put the plus or minus there to get rid of this absolute value, but that's it. We're done, and that's the general solution to that differential equation. Now let's move on to the particular side of things. So we have an initial condition, and we shouldn't have a c value left. So let's start by plugging in 1, 9 for x and y. So what's going to happen here is the y is 9 in this ordered pair. So I like to start with parentheses, 6, and then x is 1. So we're going to plug that in, squared plus c. And now you can see how this is easily going to turn into. And it is not always this easy to solve for c or to manipulate it, but in this case it is. And you would just have to use some algebra, no additional calculus, to solve for c or to algebraically manipulate it, similar to how we did under the general solution. But we have found our c value to be 3. So let me write out the equation one more time using our newfound c value. And like I said, here we are lucky. There's no algebraic manipulation needed because we already have an answer in the form y equals, and we just solved for c, so that's gone. So this is actually going to be our final answer for the original differential equation with the initial condition x equals 1 when y equals 9. So we used that initial condition in order to lead us from this to this, and you can see the difference is we have evaluated for c. So the difference there is only using the initial condition to get to the solution. And that is an example of, and we have solved these two now. So like I said, you can use the third one as practice if you would like. And that's all I have for you for this video. If you have any questions, please leave a comment or email us. If not, I hope you have a great day, and I will see you in the next video. Thank you very much, everyone.